Okay. Hi, everyone. I'm Brandon. First, I'm kind of the odd man out because I'm still an academic. And then also, I'm actually an experimentalist in this quantum error correcting section. So, what I worked on for the duration of my PhD, which I finished about a month ago, was actually trying to develop photonic interconnects for atoms. And then this project was a collaboration with MIT that I worked on in order to kind of figure out what's reasonable for rates as well as fidelities, and then what the hardware requirements would look like for that. So first, we kind of all understand that modular quantum computation would be extremely beneficial for a lot of our systems, and this was something that people knew about a long time ago. This is a paper from 2013 with this kind of like kind of infamous, I guess, picture of this cross-connect interconnect from a Chris Monroe's group, where they imagined having a bunch of individual QPUs that were then connected by these photonic links, and kind of, like 10 years later, it's still like a distant challenge, and this is like something that's still pretty hard. And now more recently, these neutral atom quantum computers, which are the systems I work on, are showing that we can actually get to number of qubits that may not need modular quantum computation, but still it would be a very important step in order to scale up the number. So here's the kind of systems I work with, where we're able to trap individual neutral atoms in optical tweezers. Then using Rydberg excitation, we can perform high fidelity 2-qubit gates, as well as performing transport. Here's a picture from the Caltech group and the Andres group at Caltech, where they're able to actually trap 6,100 qubits in one system, where they also demonstrate kind of state-of-the-art fidelities. And it does show that these systems can scale to very large size, and this is also something that, like, for example, Quera is working on, and these are things that are probably reasonable in the future to get to 10,000 to maybe 100,000 qubits. But even then, people are already starting to think about how to make these things modular. And this is something that's kind of built up over time, and now we have proposals coming out like every other month on how to make modular quantum computers using neutral atoms. A lot of the proposals rely on optical cavities to enhance the collection efficiency, which I guess everyone here kind of knows is a very important thing when trying to increase your networking rates. And these systems all rely on this fast atom photon entanglement generation. We've heard from NanoQD before, and then kind of what I'll talk about is this work between Harvard and MIT, where we envision kind of what kind of rates we need and what kind of fidelities we need. Now, if we look at the current state of the art for entanglement generation rates, we can kind of plot it. So these are all older numbers. So also there's probably people in this room where they have a better number, and you can tell me later. But I know that this is kind of old, but this is still around where the state of the art is. The fidelities we can reach are somewhere above 90, but the rates are around 100 hertz. And this is something that really needs to be addressed, and we're kind of working on that in our lab and kind of across the world. And if you look at all of these proposals, their numbers are like 2 orders of magnitude higher in rate, and then the fidelity is, if you like zoom in a lot, you can see it's 99.9%. And these are things that you can definitely write down, but would be, to me as an experimentalist, challenging. So in our paper, what we tried to think about is separate modules that are all surface codes, each one having a single logical qubit. And then we think about trying to connect these surface codes using noisy links between, namely photonic interconnects to create noisy bell pairs. These noisy bell pairs will exist at only one seam. Thus, if in order to have a logical error, you need this seam to cross your entire code distance. So this is suppressed by bulk errors, which are now these high fidelity local gates, which can then suppress your errors into the bulk and result in a better threshold for your bell state fidelities than for your local gate fidelities. And this looks something like this, where now maybe we only need a bell state fidelity of 10% as long as our local gates are high fidelity. And then the way the scheme would work is you would need around D bell pairs in order every logical cycle in order to produce this entanglement, and then you repeat this for D cycles. And many other proposals have also thought of different ways of doing this. So NanoQD, which we heard Aki talk about before, has these methods for doing distillation and transversal gates. And these are also good ways of doing it. There's different ways of doing it, and this is one of them. at Harvard and in collaboration with Quora, they've also come up with these proposals where they do concatenated distillation of codes in order to also kind of purify these Bell state entanglement rates. Something kind of interesting about this approach is they have a trade-off between the amount of buffer qubits you use for this concatenation and the networking rate and entanglement fidelity. So when this first came out, and my advisor, he had them give a talk, he said, Brandon, you need to look at this. This will make your life easier, but it also just makes my life sound harder when you need 10,000 more qubits in order to sacrifice the networking. So I mean, one thing we're thinking about is maybe there's a different optimal system where instead of using optical interconnects that are faster, you can also increase the size of your system. Another direction that people are taking, so this is work from UIC, there's specific algorithms that require less transversal gates between modules. So if you find optimal algorithms where you really don't need that many non-local connections, you can find ways to optimize or minimize the networking requirements. And in the paper, we look at many different ways of doing this networking. One is just taking all of your atoms in your atom array and making them emit photons and putting these photons into like a fiber array, for example. And that's recently been realized in also the group at UIC, where maybe this approach could be nice because it doesn't require things like integration of optical cavities, which can be challenging. But then you can also enhance the rate by adding an optical cavity. And so this is a picture from our lab, which should be moving, but yeah, we can move the atom array inside of the lower part, which is an optical cavity. And these micro cavities are really nice because they have high bandwidth and they give you strong coupling, which then allows you to emit photons significantly faster than you would in free space. And then other approaches, which are kind of new. So last week I was at DayMop. People have been able to develop photonic interconnects where you have arrays of optical cavities working in parallel, which will then give you this parallelization while also getting the enhanced emission efficiency. So this is a picture from their work, and then this is work we've done at Harvard for fabrication of arrays of microcavities, which is also promising for increasing these rates. But I guess the main takeaway I want to kind of say is it's kind of unclear what the hardware is best right now. And it's going to rely a lot on kind of integration, I think, like figuring out how to make, whether it's ions or neutral atoms, behave well with your photonic interconnect. And then it's also kind of unclear what the best error correction scheme is. So there's all these trade-offs, and maybe that will have to be tailored to your hardware. And so trying to work on these things together is what will probably eventually happen, and people will develop different error correction schemes for different hardwares. And I think it'll be like a very interesting time in the next few years to see which one kind of, I mean, not wins out, but yeah, wins out. Okay.